In this video, we're going to see that when a series is convergent, it could be convergent in two different ways. It could be absolutely convergent or conditionally convergent. And throughout the rest of this playlist, we're going to see some interesting properties of series that are absolutely convergent and series that are conditionally convergent, and we'll see that one of the two is much nicer than the other. So let's get started. Imagine that we have this series here. We have this series of whose terms are cos n over n squared. If we take a look at the first 5 terms, we see, well, like 0.54, then negative 0.104, then negative 0.101, negative 0.0041, then positive 0.04. So we have positive and negative terms, but this series here is not alternating. So we cannot use the alternating series test, and we cannot use any of the tests that we saw that applied only to series of positive terms. So we need another tool to study the convergence of these series, and that's what we're going to do in this video. Well, a series is called absolutely convergent if the series of the absolute values, so the series of the absolute values of the an, is convergent. And you see now, when we look at the series of the absolute values, all the terms are positive. And that means that now we can use the tests that apply only to series of positive terms. And that's great because we have the basic comparison test, we have the limit comparison test, and they were very, very helpful. So now we can apply it to these series. Very good. That's, it's nice. Then a question for you. Is the series given by the sum from n equals 1 to infinity of minus 1 to the n over n squared absolutely convergent? If you need some time, I invite you to pause the video, and when you have an answer, please come back. Great, welcome back. If your answer was yes, you are correct, right? If we look at the absolute value of the terms, this is just 1 over n squared, and we know that this is a convergent series. It's a p series with p equals 2, which is bigger than 1. Excellent. So things are pretty good so far. But now, can't you think of a series that is convergent but not absolutely convergent? Again, pause the video and try to come up with an example of a series that is convergent but that the series of the absolute value of the terms is not convergent. Great. So we have a very old friend, the alternating harmonic series. If you look at this one, it is convergent by the alternating series test. But when we look at the series of the absolute values, we end up with just the harmonic series. And we know the harmonic series is divergent. So the alternated harmonic series is convergent, but it's not absolutely convergent. Excellent. So if a series is convergent but not absolutely convergent, we say that it is conditionally convergent. So we've seen already an example of an absolutely convergent series and an example of a conditionally convergent series. And here we have this theorem that is very nice. And it tells me that if I know that a series is absolutely convergent, then it is convergent. And the reason why this is nice is because remember that I told you that when we look at the series of the absolute values of the terms, now all the terms are positive, and we can use basic comparison test and limit comparison test, which were very nice to use and very convenient. So what we want to do very often is, given a series, we're going to look at the series of the absolute values, study that with the tools that we have, and if we find that that one is convergent, then my original series is convergent. So, warning here, the converse is not true, right? We know that there are series that are convergent, but not absolutely convergent. So the converse is not true. And with this theorem, we can see that there are 3 types of series. Well, if we know that the series is convergent, then if the series of the absolute values is also convergent, then the series is absolutely convergent. If my original series is convergent, but the series of the absolute value of the terms is not convergent, then my series is conditionally convergent. Now, if I know that my series is divergent, Can the series of the absolute values be convergent? No, because you see, what is the contrapositive of the theorem that we have above? Well, the contrapositive says that if the series is not convergent or divergent, then the series is not absolutely convergent. So that case is impossible. And, well, my series is divergent, the series of the absolute values is divergent, we just call it divergent. So we have really three options: absolutely convergent, conditionally convergent, and divergent. Okay, so now we're going to see an example of how we use this theorem in practice, and later we're going to take a look at the proof. So remember this example that began the discussion? Well, now we're going to use this theorem to prove that this series here is actually convergent. So we're going to do the following. We're going to look at the one of the absolute values. Now all the terms are non-negative, but even more, I know how to bound the absolute value of cosine, because I know that cosine is always between -1 and 1, which means that, well, I'm going to use a comparison test to compare it. How? Well, we know that cosine of n over n squared is going to be between 0 and 1 over n squared. But the series of 1 over n squared we know is convergent, so by the basic comparison test, I know that this series here is convergent. Oh, that means that my original series is absolutely convergent. So by the absolute convergence test, I know that my original series is also convergent. And that is how we use the absolute convergence test to show that a series is convergent by studying the series of the absolute value of its terms. Now that we know how to use the theorem, it would be nice to see a proof, right? So let's get started with a proof. Well, we're going to assume that the series of the absolute values converges. And we're going to define two sequences based on the terms of my original series. So I'm going to call an plus. This is going to be an plus is equal to an if an is non-negative, is positive, and 0 if an is negative. So what this does is it looks at all the terms of the sequence an. If the term is positive, it doesn't do anything to it, but if it's negative, it just sends it to 0. And then we're going to look at an minus. And what it does is that if a number is negative, then it does minus an, which is actually just the absolute value of that number. And if the number is positive, it sends it to 0. So what this does is an plus collects the information about all the positive terms, and an minus collects information about all the negative terms. And, well, we need to try to understand this a bit more. Well, an, any term in my sequence an, can be written as an plus minus an minus. And why is this? Well, let's see. If an is positive, then an plus is just equal to an. But an minus is 0. So we're good. If an is negative, an plus is 0. And then an minus is negative an. So we have minus minus an, which is an. So good. That is perfect. Now, well, an plus is less than or equal to the absolute value of an. Why is this? If an is positive, an plus is just an, is the absolute value. And if it's negative, it's 0. Good. The absolute value is always greater than or equal to 0. And we have the same thing for the an negative. So for the one that collects the absolute value, actually, of the negative terms. Because what happens here is, well, an's are always non-negative by definition. And if an is negative, negative an is equal to the absolute value of an. So we're good. And if an is positive, this is 0. So in either case, we are good to go. So we have these very nice properties here. But look at this now. What can I do? Well, remember, I know that the series of the absolute values is convergent. So I can use the basic comparison test to conclude that the series of the positive terms and the series of the negative terms are both convergent. Oh, okay, so I know that these two things are convergent, but also look at the previous point. I know that I can write an as an plus minus an minus. And we know that convergent series are linear. So then we can see that the series of my original series is convergent, and even more. I can write the series of the an as the sum of the positive terms minus the sum of the absolute values of the negative terms. So what we have here is the sum of the an's is equal to the sum of the an plus minus the sum of the an minus. And that completes the proof. And here I'm leaving an exercise for you. Part of the proof of this is actually hidden, but not too hidden, in the proof of the previous statement. And I want you to show that if I know that a series is absolutely convergent, this is equivalent to knowing that the sum of the positive terms and the sum of the negative terms are both convergent. Here I have a little exercise for you. I wanted to show that a series is absolutely convergent if and only if both the series of the positive terms and the series of the negative terms are convergent. The proof is partially done already in the proof of the previous theorem, so you just need to fill in the gaps and complete it, but this should be quite easy to do.